Steam Systems. Welcome to this module on Steam Systems Part 1. In this session, we'll cover essential topics, including how steam is formed, the advantages of using steam, and understanding the relationships between pressure, temperature, and energy in steam systems. Let's dive into the details. Topics to be covered. In this module, we will explore various aspects of steam systems, including the formation of steam, the benefits of using steam, and the critical relationships between pressure, temperature, and energy. Locomotive boiler. A locomotive boiler is a classic fire tube boiler historically used in steam locomotives. It generates steam by burning fuel, which heats water to create high-pressure steam. This steam powers the locomotive's pistons, transforming thermal energy into mechanical motion. Compact and mobile, the locomotive boiler remains a cornerstone example of early steam engineering. Boiler house. A boiler house is a specialized facility designed for producing steam for industrial processes or building heating. Inside, it houses all the necessary equipment, such as fuel storage, burners, and water treatment systems. With an efficient layout, the boiler house is key for safe and effective steam generation, requiring regular maintenance to ensure peak energy efficiency. Modern shell boiler. Modern shell boilers, which feature a cylindrical design, are highly efficient and widely used in medium to large-scale industries. The shell boiler's compact structure houses fire tubes that heat water, minimizing heat loss for enhanced energy efficiency. Known for their robustness, these boilers are integral to manufacturing facilities worldwide. Centralized boiler plant. A centralized boiler plant produces steam or hot water and distributes it through a network to multiple buildings, making it a cost-effective solution for large facilities. Centralized plants simplify the heating process, allowing for better control over energy usage and maintenance. Boiler blowdown. Boiler blowdown is a process for removing impurities and sediments from boiler water to prevent corrosion and maintain efficiency. This routine discharge of water helps eliminate dissolved solids, prolonging the boiler's lifespan and ensuring it operates at peak efficiency. BTU, British Thermal Unit. A British Thermal Unit, or BTU, measures the heat required to raise 1 pound of water by 1 degree Fahrenheit. In steam systems, BTUs gauge the heating capacity of boilers and are essential for evaluating system efficiency. BTU calculations help optimize energy use in heating systems across various industries. Condensate return unit. The condensate return unit collects condensed steam, or condensate, and returns it to the boiler. This recycling process conserves water and energy, reducing operational costs. Equipped with pumps and storage tanks, the unit plays a vital role in maximizing steam cycle efficiency and sustainability. Electric oil heating system. Electric oil heating systems use electricity to heat oil, which then transfers heat for industrial applications. These systems offer precise temperature control without relying on combustion fuels, making them ideal for industries where cleanliness and safety are top priorities. Thermal oil heating system. A thermal oil heating system heats thermal oil in a closed-loop system, enabling high-temperature operation without high pressure. This makes it safer and highly efficient, particularly for industries like food, pharmaceuticals, and chemicals that require consistent, high-temperature heating. Steam plate heat exchanger. Steam plate heat exchangers transfer heat from steam to another fluid for heating purposes. With a design that maximizes surface area, these exchangers ensure efficient heat transfer. Common in HVAC, food processing, and chemical industries, they provide indirect heating while protecting the heated fluid from contamination. Supervisory control and data acquisition, SCADA. SCADA systems monitor and control industrial processes, including steam systems. SCADA collects real-time data, enabling operators to optimize system performance and troubleshoot remotely. It's essential for managing boiler performance, pressure, and temperature, enhancing efficiency and safety in steam systems. Building Management System, BMS. A building management system, or BMS, automates and monitors building services such as HVAC and lighting, including steam systems. BMS helps reduce energy consumption, optimize heating, and detect inefficiencies, supporting sustainable and energy-efficient building operations. Energy Management System, EMS. An energy management system, or EMS, is a set of tools to control and optimize a facility's energy use. In steam systems, EMS tracks consumption, identifies energy-saving opportunities, and boosts boiler efficiency, aligning with sustainability goals and regulatory compliance. Petrochemical plant and process. Steam is crucial in petrochemical plants, providing energy for high-temperature processes like heating, distillation, and chemical reactions. Efficient steam systems reduce production costs and contamination risks, making them essential in the petrochemical industry. Petrochemical products. Steam plays a key role in producing petrochemical products, such as plastics and fertilizers. By providing consistent heat, it ensures quality control and precise temperature management for complex chemical reactions, improving both product quality and production costs. Production of steam. Steam is produced when water reaches its boiling point, creating pressurized steam in a boiler. Efficient steam production requires the right boiler pressure, temperature, and water quality. Steam production is vital in various energy and industrial processes. Heat energy transfer. Heat energy transfer in steam systems involves moving heat from steam to another medium, like water or air, for heating or power. Steam's latent heat makes it ideal for efficient energy transfer, which is central to heating and power applications in steam systems. Textile and paper industry. The textile and paper industries rely on steam for processes like dyeing, drying, and fabric finishing. Steam's ability to provide large quantities of heat efficiently supports high-volume production, reducing operational costs and enhancing productivity. Rubber curing factory. Rubber curing factories use steam to heat rubber, facilitating the vulcanization process. This controlled heat application ensures consistent product quality, reducing energy costs and improving production speed. Brewing industry. In the brewing industry, steam heats and sterilizes brewing vessels, ensuring quality processes like mashing and fermentation. Efficient steam systems lower energy costs, supporting sustainable practices and enhancing the final product's quality. Steam fire extinguisher. Steam fire extinguishers use steam to displace oxygen, effectively suppressing fires in specific industrial settings. This method is ideal in confined areas where traditional extinguishers may not be suitable, minimizing damage to sensitive equipment. Humidification. Steam humidification adds moisture to the air, improving comfort and air quality. Common in commercial and industrial environments, steam humidifiers maintain optimal humidity levels, reducing respiratory issues and static electricity. Pan-type humidifier. A pan-type humidifier evaporates water from a pan to add moisture to the air, commonly used in HVAC systems for medium to large spaces. Pan-type humidifiers are simple to maintain, helping ensure consistent indoor humidity and comfort in commercial and industrial spaces. Topics to be covered. In this section, we will cover several important topics related to steam systems. We will describe a useful measure of boiler efficiency and the impact of boiler size on efficiency. Next, we will discuss the effect of working pressure on efficiency and describe the impact of air and non-condensable gases in the steam system. We will also cover the basic steam circuit and list the benefits of steam and condensate metering. Finally, we will identify the benefits of steam and condensate manifolds. Firing equipment. Firing equipment in steam systems consists of burners and associated components that supply fuel and air for heating the boiler. The efficiency and design of this equipment are crucial to overall boiler performance. Proper maintenance and calibration ensure that fuel combustion is both safe and efficient. Common types include gas, oil, and dual fuel burners. High-quality firing equipment optimizes fuel use and minimizes emissions. Comparing old and new boilers. Comparing old and new boilers reveals significant differences. An older boiler is typically larger and bulkier, taking up more space, and consists of multiple components like pumps and piping. The visible pipes and wiring can lead to a potentially messy setup. In contrast, a new boiler is modern and compact, often designed as a single unit, minimizing the number of components. The piping and wiring are more streamlined and organized, providing a clean and modern look. Additionally, modern boilers are often more energy efficient than their older counterparts. Water hammer. Water hammer is a shockwave phenomenon that occurs when steam suddenly condenses, creating high-pressure waves capable of damaging pipes and equipment. It's often caused by poor drainage or sudden valve closures. To prevent water hammer, systems need proper design, adequate drainage, and regular condensate removal. This prevention strategy improves system reliability and extends equipment life. Steam pipes. Steam pipes are essential for transporting steam from the boiler to different usage points. They must withstand high temperatures and pressures, typically requiring materials like steel or copper. Insulating steam pipes helps reduce heat loss, enhancing efficiency. Proper sizing and upkeep of these pipes help avoid pressure drops and maintain steam flow. Good piping design ensures effective steam distribution. Non-condensable gases. Non-condensable gases, such as air, can accumulate in steam systems, reducing heat transfer and creating hot spots. These gases can also cause corrosion and decrease system performance. Removing non-condensable gases is essential for efficient boiler operation. Air vents and vacuum pumps are typically used to expel these gases, which leads to better heat transfer and longer equipment lifespan. Thermostatic air vents. Thermostatic air vents are devices that release trapped air from steam systems to improve heat transfer efficiency. They work by sensing temperature differences, opening to release air when needed. Installing these vents prevents air pockets, ensuring even heating and system efficiency. Thermostatic air vents are commonly used in radiators and heat exchangers, promoting reliable system operation. Pipe erosion. Pipe erosion in steam systems results from high-speed steam or condensate flow, which wears down pipe surfaces. This can lead to leaks and reduced efficiency. Causes of erosion include poor design, inappropriate materials, and insufficient maintenance. Preventing erosion requires choosing the right materials and maintaining system pressures. Managing pipe erosion is vital for long-term system integrity. Basic steam circuit. The basic steam circuit involves steam flowing from the boiler to its usage point and back as condensate. It includes key components like steam pipes, traps, and condensate return units. A well-designed circuit minimizes energy loss and ensures efficient steam distribution. Steam is used for heating or power, then condensed and returned to the boiler, enhancing overall efficiency. Steam and condensate loop. The steam and condensate loop is the complete flow process from steam generation to condensate return. This closed-loop design recycles condensate, minimizing water and energy loss. Essential components include steam traps, return lines, and pumps. Efficient condensate recovery lowers fuel and water costs, making a balanced loop crucial for high performance. Boiler crown valve. The boiler crown valve, positioned at the boiler's top, controls steam discharge. It plays a crucial role in managing pressure and ensuring safe steam flow. Crown valves are large and robust to handle high temperatures and pressures, and they need regular maintenance for safety and efficiency. Wire drawing machine. In steam systems, a wire drawing machine can help control steam pressure by narrowing the flow path, creating a pressure drop. This process protects downstream equipment and maintains efficiency. Managing steam flow velocity and temperature requires careful regulation with specialized valves. Steam traps. Steam traps remove condensate and non-condensable gases from steam lines, maintaining heat transfer efficiency. They prevent issues like water hammer and improve steam quality. Various types, such as mechanical and thermostatic traps, are chosen based on application needs. Routine inspection and maintenance reduce energy loss and operational costs. Steam flow meter. Steam flow meters measure steam flow rates, providing data crucial for energy management and efficiency. Accurate flow measurement helps track costs, balance systems, and optimize efficiency. Different types of meters, such as vortex and turbine, are used based on application. Monitoring steam flow supports efficient resource use and system troubleshooting. Steam plant efficiency. Steam plant efficiency measures how well a system converts fuel into steam energy. Higher efficiency means lower fuel consumption and reduced emissions. Factors like boiler design, operation, and maintenance impact this efficiency. Improving steam plant efficiency is essential to cut costs and reduce environmental impact, especially in energy-intensive industries. Direct acting control valve. Direct acting control valves regulate steam flow by responding directly to process changes without external power. These valves are simple, reliable, and used for pressure and temperature control in smaller steam systems. By ensuring precise steam distribution, they enhance energy efficiency. Pilot-operated valve. Pilot-operated valves control pressure accurately and are ideal for high-pressure applications. Using a smaller pilot valve to control the main valve, they reduce wear and improve efficiency. They are common in industrial settings where reliability and precision are key. Pneumatically operated valve. Pneumatically operated valves are controlled by air pressure, allowing precise steam control and suitable for automated systems. Their fast response and remote control make them ideal for large-scale operations, improving process control and safety. Manual control valve. Manual control valves allow operators to adjust steam flow manually, offering simple, Low-cost control for non-critical applications. Though not ideal for automation, they are reliable and low maintenance, suitable for small-scale or backup operations. Self-acting control valve. Self-acting control valves adjust steam flow based on changes in pressure or temperature without external power, making them cost-effective for smaller applications. These valves automatically balance system demand, enhancing energy efficiency. Jacketed piping. Jacketed piping consists of an inner and outer pipe to insulate or heat the steam, commonly used for high-temperature applications. This design minimizes heat loss, essential for precise temperature control in industries like chemical and food processing. Copper tubing. Copper tubing is often used in smaller steam systems due to its excellent conductivity, corrosion resistance, and durability. It's ideal for low-pressure applications, lightweight, and requires minimal maintenance, making it popular in residential and light industrial settings. Steam manifolds. Steam manifolds distribute steam from a central source to multiple points, allowing controlled supply to different locations. Manifolds improve distribution efficiency and simplify system management, reducing energy waste by allowing isolation without system disruption. Condensate manifold. Condensate manifolds collect condensate from various sources, directing it back to the boiler for reuse. They enhance efficiency by maximizing condensate recovery, playing a vital role in sustainable steam operations. Properly designed manifolds improve energy efficiency and reduce costs. Thank you for completing Part 1. Stay tuned for Part 2. For more details, please contact TSD Office Engineering GHG. We appreciate your interest in ESG initiatives.